In this video, we're going to do a couple more practice problems dealing with the units of the derivative and interpreting the derivative in the context of a real-life problem. So the first example, we're going to have Q equals F of P gives the number of pounds of sugar produced by a manufacturer when the pound is P cents. What are the units and the meaning of the statement F prime of 30 equals 50? So first, let's maybe identify what our variables are. The independent variable here, this is like our x, is going to be equal to P, and that is going to be the cost of a pound of sugar. The dependent variable, that's going to be like our y, is going to be Q, and that is the number of pounds of sugar produced. So we are looking for F prime of 30 equals 50. And it might help to write this in Leibniz notation to say that this is going to be dq dp evaluated at p equals 30 is going to equal 50. So the units that I'm going to have here, let's do that first. Units we can think about are going to be dp or dq over dp, that's our derivative. Q is pounds produced, and P is going to be in cents, how much money it's going to be. So it's going to be pounds per cent produced. All right, so now let's think about what it means in terms of the words. So here, the derivative value is 50, and our input is 30. So we're going to say, when we're going to input P equals 30, so when the cost of a pound of sugar is 30 cents. So again, that is just saying P equals 30. When P equals 30, we're then going to say if P increases by 1, so when the cost of a pound of sugar is 30 cents, if the price increases by 1 cent, then 50 more pounds of sugar can be produced. And that is just saying that the derivative equals 50. So when the cost of a pound of sugar is 30 cents, that's saying P equals 30. If the price increases by 1 cent, then we can produce 50 more pounds of sugar. All right, next example problem, we're going to look at F of T, which is the number of centimeters of rainfall fallen since midnight. T is going to be the time in hours, and again, F of T is the number of centimeters fallen. And we're going to interpret the following in practical terms, giving units. So first, let's start with the easier problem, F of 10 equals 30. Here, 10 is our T value, 3.1 is our f value, our function value. We'll call it C here, so we can label it a little better. That's number of centimeters. So at t equals 10, so that's saying at 10 hours past midnight, and then we're going to interpret what does C equals 3.1 mean. At 10 hours past midnight, 3.1 centimeters of rain has fallen. All right, now let's think about what the inverse of that means. So let's review that the inverse, we are going to switch X and Y, or in this case, we're going to switch T and C. So here, the C value is 5, and the T value is 16. So how can we interpret this? First, we're going to say, what does it mean to be C equals 5? So we're going to say 5 hours past midnight. So at 5 hours past midnight, and then we'll interpret T equals 16. Oh, sorry, I did that backwards. Blah. C equals 5. That's the centimeters. That's saying when 5 centimeters of rain have already fallen, we can say the time is 16 hours past midnight. And that seems kind of like a more awkward way of saying it, but again, that's the idea of the inverses. We're switching the roles of T and C. Now let's think about the derivative. That's kind of the new thing in this section. So the derivative, f prime of 10 equals 0.4. Again, this is going to be a T value. This is going to be a C value. So we're going to write at T equals 10. So at 10 hours past midnight, that's at 10 a.m., then I'm going to write when T increases by 1. So that's going to say at 10 hours past midnight, if 1 more hour passes, and then we're going to say the derivative is 0.4. So that's saying if 1 more hour passes, 0.4 centimeters more rainfall will occur. So it's saying the amount of rainfall that you have in 1 hour is going to be about 0.4 centimeters. And you can word that kind of in a way that makes the most sense to you. That's what I'm going to do right there. Lastly, we have the derivative of the inverse. So note that we are now switching y and x. That's going to be t and c. So we have our input here is c, and our output is t. So it's kind of structured in the same way that we did before. Here, we're going to start with c equals 5. So we're going to say when 5 centimeters of rainfall of rain has fallen, then we're going to say if C increases by 1, Okay, then we're going to say that T equals 2. So we're going to say if 1 more centimeter of rain falls, the time has increased 2 hours. All right, and that sounds maybe a little bit awkward. So maybe let's try to reword that last sentence, especially with kind of now we have the information. So let's write that as when 5 centimeters of rain have fallen, it will take 2 more hours for another centimeter of rain. And that sounds like a more useful English sentence. So we can kind of do that for all of those. Let's think about C at 10 hours past midnight. Said if 1 more hour passes, 0.4 centimeters more rainfall will occur. We can say at 10 hours past midnight, we'll expect 0.4 centimeters of rainfall in the next hour, right? Or from 10 a.m. to 11 a.m., we should expect 0.4 centimeters more rainfall. All right, important to think about what the units are in all of this and how they are related.